Right then, this is the first of the main questions. I'm looking at page, let's grab the book here, yeah, page 354, section 24.1, transforming functions. We've had the introductory videos, now let's do the questions from the book. Right, each question is quite involved, very long. This is question 1. It says, sketch and label each of these graphs, so y equals x squared, y equals 1 over x, y equals x cubed, y equals sine x, and y equals cos x. So 6 little sketches. I've got 6 pages to show you. Now for each of these 6 sketches, it says I've got to translate each graph using the vector 0, 4. So remember, essentially that means raising each graph 4 units upwards. Is that okay? Hope you remember that. How does that go? So if I've got a general function y equals some sort of function in x, and therefore what I'm doing is taking each function like that and essentially adding 4, hence raising each graph upwards by 4 units along the y-axis. So that's very, very easy. And for each of these graphs, I've then got to sketch each one, and then I've got to stretch it in the y direction by scale factor 3. Now if you remember this from the previous introductory videos, what I'm essentially doing here is leaving the x coordinate unchanged, but multiplying the y coordinate by 3. Right, hence the 3 there. So for example, y equals x squared. So what I do is leave the x alone. I just multiply the y coordinate of each coordinate by 3, and I then just retransform the graph. Okay, so it will become clearer once I begin to work on it. So this equation would effectively be, for example, y equals x squared is the original. If I'm going to transform it, it will become y equals 3x squared, and the effect of that will be quite striking. So that's that one, for example. So I've taken a generic y equals some sort of function of x, it could be any one of these, and I'm transforming it into y equals a f of x, and of course the a value happens to be 3 on this occasion, so therefore I've got 3 times the function of x, and that will be my transform function in each case. Probably getting very glitchy this because it's taking me a long time to write a single thing. So let's just start to do this if we can. So right, let's just recall. Sketch each of these 6, move them all 4 units upwards, stretch each one in the y direction by a scale factor of 3, and then label all the equations in parts B and C. So I've got 18 things to do. Well, here's my prep. This is the graph of y equals x. The first thing I've got to do, as you can see, it's quite accurate. It's 2, 2, 6, 6. That's the graph of y equals x, and that's just a copy of the graph on the right there. If I'm going to transform it 4 units in the y direction, I'm going from 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. So that's going to be a very key point there. So that's the point 0, 4, and essentially I draw the graph through that point there. That's the lowest point in terms of cutting through the y-axis, that is, and 2, 2 will become 2, 6. So 2, 4, 2, 6 is there. Alright, as you can see, if that is in fact 2, 6, what I've done is left the x coordinate unchanged and multiplied, what am I doing now? No, raise it 4 units, sorry. So I'm going from 2, 2 to 2, 6, basically adding 4 units onto each of the y's. So that's it. Let's just draw it in, see how it looks. If I use blue, be fine. See if I get it to work. Right, let's try and draw it like this. So join that to that, like so. Extend it the other end as well. So that's basically it, isn't it, really? So that becomes the graph of y equals x plus 4. Just label that in, and there it is. Getting very glitchy. equals x plus 4y, because I moved it 4 units up in the vertical direction, say from here to here, it's basically plus 4 units. Okay, so lifting the graph of y equals x 4 units up in the y direction. So for example, the key coordinate of 0, 0 becomes 0, 4, 1, 2, 3, 4, so it's there, and the point 2, 2 becomes 2, 6, and that's there, and the point 6, 6 becomes 6, or it goes off the scale, so I'm going to leave that one alone. So let me just try and draw that one in as best I can. If I do that and come around the other way as well, not brilliant, let's just try that. Let's try that there. Okay, that's supposed to be the graph of y equals x plus 4. So essentially I've gone from 0, 0 to 0, 4, 0, 2, 2 to 2, 6, and here we have a line parallel to the original y equals x plus 4. I just lifted it 4 units up in the air. Essentially I've translated using vector 0, 4, and up it goes in the y direction. That's it. Next one I've got to do is to apply a stretch of times 3 in the y direction. So like I said before, you leave the x alone but multiply the y part by 3. So 2, 2 becomes 2, 6. Let's just plot that in. 2, 4, 6, that's 2, 6, and by the same token 2 minus 2 minus 2 becomes minus 2 minus 6, 2, 4, 6. So the effect of transforming the graph y equals x into this new graph, I become, if you can check it carefully, y equals 3x. Is that okay? So if we talk about it in a generic sense, we have y equals some sort of function of x, the generic, generic function. So there it is, y equals x, my general function, and given by y equals f of x there. So what I can do then, if I multiply by 3, I become y equals 3 multiplied by f of x. In other words, y equals 3 x's, and so it's a much steeper gradient, as you can see. So I've transformed that one quite successfully. Next one, here's the graph of y equals x squared. Again, if I translate it 4 units up in the air, the point 0, 0 becomes the point 0, 4, and the point 2, 4 becomes the point 2, 8. So I can plot a couple of points here, working in both directions, and my graph will look a little bit like this. So with me trying to draw in ever so carefully, quite difficult. And up it goes like that. And the transformed graph is y equals x squared plus 4. Okay? Getting quite difficult and glitchy that. That's it. So one more time, what I've done, I've taken my graph of y equals x squared, and then I've applied the function y equals x squared plus 4. I've translated the graph using the vector 0, 4, hence moving the graph 4 units in the vertical direction. As you can see from there to there, it's gone plus 4 units. Now here I've got to go from y equals x squared into y equals 3x squared. In other words, transform it using the function y equals a f of x, and so here the a is therefore worth 3, and if my original function is x squared, it becomes 3x squared. You see, that's how it all relates. So that's the general function after the transformation of value a, and a being 3. So what's the rule? Leave the x alone, multiply the y by 3. So that's the point 1, 1, because 1 squared is 1. So 1, 1 becomes 1, 3, so that can go there. Let's have its mirror image over here as well in the negative second quadrant. And 2, 4 will become 2, 12, won't it? Because 4 3s are 12. So 9, 10, 11, 12. Let's have the mirror image over here. Minus 2 and up to 12. I think it's about there. Really hard to see. Anyway, what's happening is the graph has become very, very pointy, and of course 0 times 3 is 0 anyway. So let's just draw this one in if we can. Quite hard, so go carefully. It's not letting me do it. There we go. Connected. move it around and up, and there, of course that should be exactly on 0, 0, but I didn't get it very accurate there. So this little graph here is a transformation, and that is has an equation of y equals 3x squared, derived from y equals AF of x. Alright, very, very easy. It effectively stretches it in the y direction, like I said in the introductory video, but with a real graph, your x squared becomes 3x squared, and it makes sense when you apply it to genuine coordinates that one can understand. Let's try the next one. Right, I'm not going to try and explain these ones. It's really difficult. However, the first one's okay. If I want to raise the graph of y equals 1 over x up 4 units, again using the vector 0, 4, so it's up 4 units. The key point here is that this branch of the graph tends towards 0, so the lowest point in this direction will be along the graph of y equals 4. So if I was to dot in the line y equals 4, y equals 1, y equals 2, y equals 3, y equals 4, so I'll just dot this in like so in both directions. I'm effectively trying to raise this whole function up by 4 units. So the function, I hope will work out okay, will look something like that, and will tend towards the line of y equals 4, and this function therefore will also tend towards the function y equals 4, and just carry on like that. So effectively I've raised this blue part of the graph upwards 4 units that way, and this too has been raised up 4 units in that direction as well. You see, it's not very accurate, it's just a sketch, but understand then, whereas the line y equals 0, in other words the x-axis becomes, if you like, the baseline, then the baseline has been raised to the position of y equals 4, so therefore the graph will tend towards touching the line y equals 4 in both directions. Alright, and in each case of course the graph will tend towards touching the y-axis or the line x equals 0 in both directions. So that's been transformed okay, it's not too difficult to understand that one. Now this one is very hard to understand. If I'm going to go for, again let's just restate it, y equals some function of x, and then I'm going to go y equals something multiplied by the function of x, and I'm told that the a value is 3. In order to stretch this in the y direction by the value of 3, the effect is this. This graph gets pulled outwards in that direction, and this part of the branch gets pulled out in this direction. So what we in fact get is something like this after the transformation. Do it in red, it looks a little bit like this. So it gets pulled out that way a little bit more, and this one gets pulled out this way a little bit more. Alright, and so the red one is essentially y equals 3 times the function of x. In other words, the equation is going to be y equals 3 times 1, which is 3, and then just divide by x. Alright, this is the transformed function, and there it is. Alright, next one. Very, very easy this one actually. So this is the graph of y equals x cubed, very classic, beautiful shape. This is the point 0, 0, because 0 cubed is of course still 0, and if I'm going to raise it 4 units in the vertical direction using the usual vector of 0, 4, there I go, lifting up plus 4 units. So 0, 0 becomes 0, 4, 1, 2, 3, 4, and the graph essentially passes through that point. So let's just draw it in blue. Again, it's just a freehand sketch, but the key thing is that is where the turning point is. Instead of going through 0, 0, I now go through 0, 4. Okay, because I've been told to raise it 4 units, I know it's going to pass through 0, 4, and that's good enough for a sketch. Okay, so everything's been stretched, lifted 4 units up in the y direction, and of course there's the y-axis there, and there's the x over there. Now, next one, I've got to multiply the y coordinate by 3, so I'll essentially end up with, oh, by the way, new equation, y equals x cubed plus 4. I hope I just did the others on the other page, can't remember. Yeah, this is going to be y, the red one, that is to say, it's going to be y equals 1 over x plus the 4, and I've already given the equation for this one. Let's just go back, make sure I've done it for this one as well. Yep, that's alright, that's okay. That's good, that's good, that's good.